This is the Group 12 Shooting Range Scoring System presentation by Brandon Denardo, Ilia Fedorenko, Christian Nering, Edgar Lopez, and Guillermo Cruz. For the agenda, we will be going over the introduction, the proposed design, the subsystems and implementation, the development and plan schedule, the budget, and the references.
Let's begin with the problem we are addressing. Currently, there are no commercial or governmental off-the-shelf system available that can automate scoring on live fire ranges. Instead, the existing process relies on manual, paper-based scoring methods. This approach has significant limitations. It doesn't store or evaluate performance data, making it impossible to track an individual's shooting skills over their career. This lack of data also means that commanders lose critical insights into the shooter's learning progression, which could otherwise support better decision-making. An automated scoring system could change this by providing a comprehensive performance profile for individuals, enabling commanders to select their most qualified personnel for high-stakes, time-sensitive operations. Now, why is solving this problem so important? The current manual scoring system not only fails to track performance over time, but also introduces inefficiencies and errors due to its reliance on paper-based methods. For the military, this means a missed opportunity to accurately evaluate and store shooting performance data for soldiers. Without these insights, commanders cannot effectively analyze individual shooting process or critique performance trends. In the long run, proper management of shooting performance is vital. It does not only impact the success of missions, but could also mean the difference between lives saved and missions compromised. An automated system, therefore, holds the potential to significantly enhance operational readiness and decision-making.
Hello everyone, my name is Guillermo Tchelebi, and I will cover the goals and objectives of this project. So, our ultimate objective is to develop an innovative prototype for a live fire range scoring system by automating the process, which moves away from paper-based methods that are prone to error and are outdated. This innovation will enhance efficiency, it will improve data accuracy, and it will provide instructors and trainees with a tool for real-time analysis and allow them to track performance in the long term. For our system goals, we will aim to build a functioning prototype consisting of a high-resolution camera for precise impact detection, a single-board computer, or SBC, like the Raspberry Pi, for processing, and an intuitive user interface, or UI, to ensure that the system remains user-friendly. We will also leverage the YOLO V8 model for bullet detection, which ensures reliable scoring in dynamic environments. We will aim to make the system battery-powered to function independently from external power sources and also makes it deployable across various locations. Weather resistance will also be applied, so it will ensure reliable performance in challenging conditions, from rain to extreme heat, addressing the practical needs of outdoor ranges. Another goal is to make the system capable of recording results against one or more small arm firing targets, so it will record results against one or multiple targets simultaneously. Which will accommodate different types of training scenarios from individual practice to team exercises. By supporting these different ranges of target types, it can also adapt to various calibers, including rifles, pistols, and shotguns. Lastly, our prototype will provide immediate results, so shooters and instructors will receive real-time feedback during the exercise, and also an after-action review, which allows them to receive detailed performance data, which includes accuracy, reaction times, hit locations, which all will be available for post-session analysis, enabling a very comprehensive performance evaluation and a long-term skill development for each trainee. Now let's move on to the proposed design for this project. Specifically, let's look into the requirements. So all requirements for this project have been provided by sponsors and have been categorized into three groups: functional requirements, usability requirements, and safety requirements. So for our functional requirements, this system will detect and determine the location of shots fired at a firearms target. The system will log shooting results for short-term and perpetual performance metric analysis of individual shooters. And the system will operate in poor weather conditions or extreme weather conditions. For the usability requirements, this system will be user-friendly for shooters as well as for instructors. The system will be portable and battery-powered for use in any firing range environment, and the system will provide valuable metrics to instructors for immediate feedback to shooters. The product will also provide the capability of long-term tracking. So we will store this data into a database, either local or on the cloud, so they are able to access all this data and keep track of every individual shooter or trainee. Lastly, we have the safety requirements, which covers that the system will warn when running out of battery, and also the system will be electrically safe for the same purpose of using in poor weather conditions to keep it safe at all times.
Now for the proposed product design. The main characteristic of our system is going to be portability as well as durability. Since our system is going to be used for travel at various different firing ranges, it must be easily transferable and deployable at these ranges. Also, our system is intended to be used in any weather condition. The system must be very weatherproof, well structured, and very durable. Now for the system composition. The system will include a high quality Arducam Raspberry Pi camera that is used to lively recognize bullet holes patterns through any lighting environment and any weather environment. We will also be using a Raspberry Pi 4B, which will be the centerpiece of our electrical system for our prototype. Then the user will have to interact with the system to upload soldier data and also provide an after action report. This will happen through a easy to use user interface. All components will be powered through an onboard power supply with the optional capability of plugging into a 120-volt AC source.
Hello, my name is Christian Nering, and I'll be going over the block diagram for this project. The block diagram will consist of three main components. These will be the data acquisition, the portable prototype, and either the single board computer or the laptop. Data acquisition for this project will be acquired using a camera. This camera would be pointed at a firing range target and would acquire vision data. This data would be passed through the YOLO V8 model, and that is how the system would differentiate targets and bullets onto a target. As for the portable prototype, this prototype would use a waterproof housing. It would use a secure mounting solution to keep it in place with bullets being fired in its near vicinity, and it would also have an intuitive user interface. As for the last component, we would use either a single board computer or a laptop to integrate the user interface as well as the data storage for different shooters as well as different instructors. This right here is the state diagram for our project. The unit would consist of a power switch that would activate the battery and power the whole system. Once the system's on, it would wait for a user input. This user input would be some sort of instructor ID or shooter ID to differentiate who is logging in. The system will validate the user. If the user cannot be validated, it will be sent back to the login screen and wait for the user input once again. Once a user has been validated, it would wait for the session to start, and it would be started either by a shooter or an instructor. Once the session's been started, all of the components will be activated and the vision model will run as the camera is pointed at the target. The session will run all the way through and the shooter will shoot all of the targets. The system would collect and store all of the data and of course run the data through the YOLO V8 image database, and it would score the round based on the shooter's results. At the end, it would give a shooting feedback and potential improvements.
So this slide is primarily aimed at the prototype housing. As of right now, this is just a 3D model of how we would like the design to look. Um, so the design itself would be a weatherproof outside housing, and the Raspberry Pi 4B would be in its own respective case within the housing itself, which would be weather sealed from outside elements. Um, and there would be space within the housing for the other components. As you can see on the image, there would be a slot for the camera. So that way the instructor for the firing test would direct the camera towards the range and towards the target. So that way there is clear visuals of the target itself for recording and detection of the actual projectiles. And there would be the case for ease of removal for maintenance or just in case the Raspberry Pi breaks. They can easily pull out the case for the Raspberry Pi, swap out the board, pop it right back in, and theoretically it should work. Obviously, the board itself would have to be pre-programmed with the already given models. So that is down to the NETC to figure out how they would produce those in the future. Um, and as the idea is to make the housing to where it is weatherproof under various conditions. So it could be extremely cold, extremely hot conditions, and it should work under all those conditions. So as of right now, this is just a 3D model, a representation for purposes of our current presentation. And this is an ideal way that we would like the prototype to look, but this would be subject to change as time moves on and requirements do change.
As for the prototype hardware of this project, it'll have two main characteristics, the electrical and the mechanical. The electrical side will consist of the Raspberry Pi 4B. This will be the main computational unit for the system, and this will be running all of the YOLO V8 models and acquiring all of the image data. The image data will be acquired by the Raspberry Pi camera module 2. With this high quality camera, we'll be able to capture all of the images necessary to differentiate targets as well as bullets onto the targets and score their locations on that target. And as for the electrical power management, we'll use a Crave power bank to supply the system with power for its portability. As for the mechanical characteristics, we will supply a waterproof LED with a light block, and this will ensure proper lighting in poor conditions for the targets. And the enclosure will also be waterproof for use in poor weather conditions anywhere outdoors.
Here we dive deeper into user interaction and data communication aspects. The user interface will be intuitive, accessible via a web app or touchscreen, allowing users to view live feeds, adjust detection thresholds, and review detected anomalies. For data communication, GPIO and USB or CSI cables will ensure seamless connectivity between subsystems, while external communication enables optional data upload to the cloud for remote access. This ensures the system that is not only functional but also user-friendly and versatile.
Now we are going to talk about subsystem 3, which is the prototype software. First, you need to train your model to actually set a good baseline for your software and for your model hyperparameters. We have to obtain our full data set of our images of our TransStar 2 targets. We have to annotate all of our images and split them into three subsets for actual training. The first subset is the training subset. That's about 80% of our full data set, along with our validation and our testing subset, which is about 10% each. We upload these three subsets to our YOLO V8 model, and then we train our model. There are some parameters that we can adjust, and the main parameter is called epochs. Epochs is the amount of iterations that your model goes through to train. It'll go through your subset however many times you set it, and if you set your epochs too high, your model will run through your actual data set too much and it'll overfit your actual data. But if you set your epochs too low, your model won't have enough time to actually tune its actual hyperparameters well enough. So you have to find that good middle ground, and this will take a lot of time and a lot of model training to get a good model result. Once we get an acceptable output file for our model, where we have good loss, we have a good confusion matrix, and our model is actually working well, we will take that output model result and use it for our Raspberry Pi for live running. There are a few modules that we have to focus on throughout this process. The first one is our software to actually interface our camera for capturing live objects. Next, our system must have enough processing power to be able to execute all these commands and receive and process live data. Lastly is our user interface. This will be used to upload soldier data and also provide an after-action report of the live data results. Lastly, this process is going to take a lot of testing and tuning. We're going to have to tune our model a lot and use it in different weather environments and test it in different lighting environments and also environments like rain. So this will take a lot of time. Even though it's not that many tasks, it will take a lot of time to test and tune our model and develop our software efficiently.
Now that we have each different subsystem for our prototype, we need to discuss subsystem integration. So the primary goal of subsystem integration is essentially to combine the hardware, software, and design elements of the system into a unified functional prototype. So this involves addressing interdependencies, resolving conflicts, and optimizing performance to create a seamless user experience. For the integration process, we have it split up in different phases. First, we have the preparation phase. So for this phase, each subsystem, including housing, hardware, software, and database and storage, will be individually tested to ensure that each is functioning properly. We will also clearly define the interfaces and protocols for communication between subsystems. For our second phase, the physical integration phase, we will incorporate the hardware, which is the Raspberry Pi, the camera, the power bank, into the housing and mount the system on a tripod. We will also ensure that the power supply, LED lights, and data connections are wired securely and efficiently. For our third phase, the software integration phase, we will integrate the YOLO V8 model into the Raspberry Pi for the real-time image processing. We will also connect the system to the database to log shooting results and metrics for analysis, and we'll finalize the user interface for real-time feedback and control. For our system validation phase, we will conduct trials to verify the system's ability to detect and log bullet impacts, analyze performance, and present results via the UI. We will also test the system under various weather conditions to ensure durability and accuracy as intended. And finally, for the optimization phase, we will fine-tune settings such as detection thresholds, lighting conditions, and data storage protocols to enhance system performance, and we will address any issues identified during testing to improve reliability, user experience, and ease of use. So some key challenges that we may face are synchronization. So this would be ensuring the data flow remains smooth between the camera, the SBC, and the database. We will also face the durability issue, which is maintaining system functionality in outdoor conditions. for which we will use the weatherproof housing and sealants for exposed components, and the performance accuracy, which is minimizing false detections by the Yellow V8 model, for which we'll continuously train and validate the model with diverse data sets. All this will give us a functional prototype, which will be an integrated system capable of scoring and logging the shooting activities. It will give us a very flexible design that will be able to be scaled or enhanced in regarding future applications. And it will give us a very, very user-friendly interface that facilitates ease of operation and gives us immediate feedback, which is what we want going from the paper targets system.
In our testing phase, we plan to evaluate the functionality of each subsystem, such as camera, imaging, and TPU acceleration, and verify the power supply sustainability. Calibration will include fine-tuning the cameras for optimal image quality and AI software to reduce false positives. Finally, validation will involve end-to-end testing with simulated scenarios to ensure anomaly detection works as intended. Using benchmarks for AI performance, we aim to validate our system's reliability and efficiency.
Hello, my name is Edgar Lopez, and I am an electrical engineer on this project for the NETC firing range. I will be going over the scheduling, and I will be starting with the current tasks that we're currently undergoing. So the first task and the most important one is that the project is currently in a prototype stage, and we need to actually put the model together and test the previously made model from the previous team from over the summer in order to evaluate whether it could actually recognize the targets. We plan on trying to complete this by the 6th of December. Another side project that we got going on is we're checking to see if the current board that we have, which is the Raspberry Pi 4 Bravo, is capable of withstanding the computational load that it currently undergoes when running the AI model. Another task that we have on hand is getting a license for Google Colab in order to actually run the model, since we can't physically run the model on our computers, the hardware itself, because it's been known to cause issues and actually brick your device if you try to run it outside of a proper environment. So we plan on trying to have this licensed by the 6th of December. The replacing the single board computer is, we set an arbitrary date of the 7th of January, just in case we realize that we don't need to change the board. So we're just setting that as our date. Documentation. This is an ongoing process that we do within each stage of our project. So we record all codes, libraries, and annotate hardware and their respective prices to stay within budget. So this is, we set a date of the end of the next semester to kind of enclose the whole entire project, and it's an ongoing thing that we have to get done. And collaboration and insight. We're constantly staying in communications with the prior team, because there are aspects of the project that we are still trying to learn, as in how they uploaded all their data into the Yellow V8 model, and we have an idea of how we're doing that. We did our own research apart from the meeting with the previous team, so we have an idea how we're doing that, but we're staying in communication with them regardless to stay on top of that. That, again, is set for the end of next semester, because it's an ongoing process, and we plan to do this throughout each aspect of the project. And we're going to be monitoring the progress and managing timelines, so that way we don't fall behind, and we have a working prototype by the end of next semester. Now, the next thing that we plan on looking over is the milestones that we have set forth for ourselves. So that's including from now all the way up until the end of next semester. Uh, our milestones are, well, the first one that we have set is to actually assemble and test the prototype. As of right now, we have a possible candidate for a new camera, and so we want to put together the model that does work at the moment, or we believe to work. Uh, from when we spoke with the previous team, they mentioned that there was time constraints in what they were able to get done by the time they got parts and everything like that. So we basically have to put the whole prototype together and test the model and make sure that it actually recognizes the target. So the due date we have set for that is the 6th of December when we plan on doing our demo. And then our next step would be to upgrade the SVC if need be. So I would put this could be a possible milestone if we come to the realization that the current board itself can not withstand huge computational loads, because the purpose of this is to recognize multiple different kinds of projectiles within one sitting, so within one recording. So we want to make sure that the board itself could withstand that kind of load, and it has a TPU to actually handle the AI acceleration part of it. So we want to make sure that everything is within spec and that can handle without being unstable. And the due dates we have for that as well is we will possibly decide by the 6th of December whether we need to make improvements or not, judging by when we actually add the model onto the board itself in the prototype. Our next big step, which we are actually looking into, is enhancing the camera system. At its current state, the previous team mentioned that the current camera might not be enough to record the projectiles in their current state, so we have to actually upgrade, and we're looking at cameras that are compatible with the Raspberry Pi single board computer to mitigate instability. So if we can find, we found possible candidates that will work with the Raspberry Pi and actually help with the AI and machine learning aspect of it. So we plan on doing that by the 7th of January, judging by when we get the targets, when we get the Google Colab license, and we can get that going. And once we test everything in its current state, we'll decide whether we need to even go that far or stay on our current camera and board orientation. And our next thing would be to train model with the new data. So I set this for the 17th of January, but this is something that constantly has to be done. The previous team mentioned that they put over 800 images of data to train for one single projectile. So, and that's a minimum. Normally, from YOLO V8, the model is built off of continuous uploading of data points. So could be 800 images, could be 1,000 images, could be more, judging by how accurate it becomes at that certain point. So we want to spend the most time doing this. The hardware aspect of it should be the beginning stages. So maybe middle of January, we plan on having that part pretty much ironed out, and then the vast majority of the time is actually training the model to recognize all the different projectiles and targets. So for the sake of short-term milestone, I set the date for January 17th, 2025, and it's very important. There's a very important step in the actual model, so we set the most time frame for this, and yeah, that's basically our milestones or our current tasks. As time moves on, these will change and we will have to add when needed. Thank you.
Now we are going to talk about our system budget. Our proposed budget by our sponsor, the NETC, is $2,500. Currently, our prototype consists of a Raspberry Pi 4B module. We're given two different cameras, the Pi Camera Module 2 and the ArduCam camera. We also have a TPU accelerator, which is used for AI acceleration of signals, a tripod for our prototype, a camera housing to protect our camera from different weather environments, a waterproof LED light block, and a Crave power bank. This is our current components used for our system. As we conduct more testing and more research, we may upgrade some of these components in the future. The links shown are the references we use for our project and to support our research.